Hey guys, today we're going to be talking about problem 210, course schedule 2, and it's a level medium on Leetcode. As you can see, a ton of companies ask this in interviews, so it's definitely important to understand because its concepts can be applied to many other similar questions. So the question is, there are a total of n courses you have to take labeled from 0 to n minus 1. Some courses may have prereqs. For example, if prereqs I equals AI BI, this means you must take the course BI before the course AI. So given the total number of courses, num courses, in a list of the prereq pairs, return the ordering of courses you should take to finish all the courses. If there are many valid answers, return any of them. If it is impossible to finish all courses, return an empty array. So what could this mean? Let's go through the examples. If the input number of courses is 2 and the prereq is 1, 0, so that means 0 is a prereq to 1, the output must be 0, 1, and the explanation is because you have to take course 0 before you take course 1, so this is a valid ordering of the result. In example 2, the number of courses we have to take is 4, so 0 to 3, and here's the prereqs list, and as you can see, 0 is a prereq to 1 and 2, 1 is a prereq to 3, and 2 is a prereq to 3. So a valid ordering of the output is 0, 2, 1, 3. And I'll go through this later, but a good way to think about this is, for example, you take pre-algebra before algebra. So if pre-algebra is a prereq to algebra, you want that to be displayed in your final output such that the pre-algebra is before algebra. And this can go similarly for, pre-calc, calculus, geometry, linear algebra, and then probability, and any other harder courses. And not all courses are prereqs for each other. For example, you can take, or at least at my school, I believe you can take like a simple probability course, or you could take discrete math. And those two, you don't necessarily need to take one or another first, and you can take them at the same time. So that's one example. Or another good example, maybe a better example, is you can take, similarly at our school, you can take 3D calc and discrete math at the same time. So there are examples where you will have a ton of courses, like 10 courses, but not all of them are prereqs for each other. So you need to keep this in mind during the problem as well. And then example 3, this is a good example of what I was talking about, kind of. Well, I guess in this case there's only one course and there's no prereqs, so, well, I guess the problem is just asking us to return 0, which is just that one course to take, right? Because there's no other courses you need to take before that one course. But let's say, for example, if the num courses is like 10 and there's no prereqs at all, we can simply return 0 to 9. So kind of similar. Okay, so I'm going to be coding this in Python. And before we jump into it, let's talk about the formula or the algorithm we want to use. So for this question, it's a typical classic topological sort problem. And that is how we're going to approach it. And what is topological sort? Well, I'll explain it here. Okay, so what is topological sorting? Well, according to Geeks for Geeks, topological sorting is for directed acyclical graphs, and it's a linear ordering of vertices such that for every directed edge uv, vertex u comes before v in the ordering. What does this mean? Well, basically, say we have vertex u is 6 and v is 3, and edge uv is the edge between 6 and 3. It means that in the topological sort, 6 needs to be before 3 somewhere in the sort. As long as it's before 3, it's a valid topological sort. So what does that mean, and what is a valid topological sort for this graph? Well, simply put, a valid topological sort is just 7, 6, 5, 4, 3, 2, 1, 0. And why is that? Well, as you can see, 7 comes before everything else in the graph, so it's at the front of the topological sort. And then after that, you see that 7 has to be before 6, right? But 6 needs to be after 4 and 3. And it is, so that checks out. And then similarly, 5 needs to be after 7 and before 2 and 4. And it is, so that checks out too. And then 4, okay, we can just place 4 next, because 4 just needs to be after 5 and 6, but since 4 is pointing to nothing, there's nothing it needs to be before, so that's fine. And then 3 needs to be after 6 and before 1, that checks out. 2 needs to be after 5 and before 1, that checks out. 1 needs to be after both 2 and 3, checks out. And the 0 needs to be after 1. So this is one valid topological sort. And to approach the problem, let's erase this. We will do topological sorting based on n degrees. What is an n degree? An n degree is basically how many edges are pointing towards the node. So, for example, 7 has an n degree of 0 because nothing's pointing to 7. 5 has an n degree of 1 because 7 is pointing to 5. But 4 has an n degree of 2 because 5 and 6 are both pointing to 4. So the rule of thumb for topological sorting is whatever has an n degree of 1 for sure goes to the front of the finished result sort. And we mentioned earlier that topological sort only works on directed acyclical graphs, and that basically means, for example, if your graph is circular, there's no valid topological sort, right? Because there's no ordering such that everything that's supposed to go before goes before and everything after goes after because it's circular. So back to the n degrees. So we know 7 has n degree of 0, so we put it at the front of the result, right? And then we can kind of think of it as, now that we've taken care of it, we can erase it from our graph. And now we're left with 5 and 6. And then we apply the exact same mentality of, oh, whatever has n degree of 0 can come to the front of the result. So now we see 5 and 6 both have n degree of 0, so we can put it in front, right? And then you can erase those because we've taken care of them. And since those are out of the graph, we can erase the edges as well. And then we see that, oh, like 4 has n degree of 0, and so does 2 and 3. So we can add those. And then you erase those nodes because we've taken care of it. Then 1 has n degree of 0, erase 1, and then 0 has n degree of 0 now. And this is indeed a valid topological sort of our graph as well. And, well, based on this logic, we can proceed with the question. So now let's go back to Leetcode. Now that we've explained the algorithm, let's get right into the coding. So we need to first cover our corner cases, which is if the num of courses is less than or equal to 1, then we just return that course. And if the length of the prerequisites equals 0, so there's no prereqs, then we can just simply return an array of the courses. Just like that. Okay, so those are the corner cases. What was our next step? We want to build a graph, first of all, which is an adjacency list. And not only that, but as we can remember, we want to find the n degrees of each vertex in the graph. So we can instantiate n degrees, which it will be a dictionary. And at first, it'll just be n degree of 0 for every vertex. And we know here that we are already given the num courses, so we can just use that as our classes or vertices. And then here I am instantiating the adjacency list, which will also be a dictionary. And it'll be a dictionary of lists, and the list will just contain all the nodes that whatever vertex you're looking at is pointing to. So let's go through the prereqs here. So we can extract the course and the prereq out of the prereqs list that were given in our input. And then we want to append it to the adjacency list. prereq.append course. Okay, so this means that the prereq, now we're appending the course to the prereq, so in the end it'll be adjacency list, and each prereq will point to, or will have a list of its courses that need to be after that prereq. Got it? And this will be a dictionary for fast lookup times. And in degrees of the course, we simply plus equals 1 because we now know if a course has a prereq, it must mean that something is pointing to the course, which means it has an extra in degree. Okay, so what was the next step after this? Well, we wanted to add all the vertices with an in degree of 0 to the front of the result, right? So let's store these vertices with 0 in degree into a queue. It doesn't have to be a queue, but for our sake of topological sort, and I think in general, people use a queue to store the sources, but you know, it could be kind of like a list or stack as well, I believe. Just something to store the vertices with a in degree of 0. So queue and then we go through the number of in degrees that we built earlier. And if the num in degree is 0, we know that we can add it, so we append to the queue. Okay, so now we have like basically all of the front nodes, or front vertices that can be at the front of our result, right? So we want to create a result list. So that's the empty list. And then while the queue is not empty, we can pop from the queue and we can append it to the result list. Right? So now we're just appending it to the front of our result. And then the most important part is that once we append something to our result, remember we kind of get rid of it. And what I mean by that is we want to subtract 1 from all of its neighboring or like children in degrees. So subtract 1 from the in degrees of all its children, because nothing points to the children anymore because we've taken it out and we've considered it in the result already. So for each course in the adjacency list of whatever prereq we were looking at, we simply just subtract 1 from the in degrees dictionary we built earlier. And then we need to do a check that if now that becomes a new front of the result, because if that hits an in degree of 0 now, then we can append that course to the queue now. So basically, the summary is we start in a queue, we pop whatever has an in degree of 0 to our result, and then each child of that vertex that we just popped off, we minus 1 in degree from that child. And if the child's in degree hits 0, we now append it to the queue because we know it's a valid new front of the result, right? And then at the end, we just want to do a safety check to make sure it's like a valid graph, you know, and there's no circles and there's the right number of courses in our result. So if if length of result list, if it's not equal to the number of courses given, then we can return empty list. And else we just simply return result list. And I believe that is all we need for this question. So it's not as complex as one might think when first looking at it, but let's run it to make sure it works. Okay, let's first run the code here. Oh, it's default dict. Oops, so adjacency list wrong. Okay, my typing sucks, low-key. Oh my god. Adjacency list. Wait. Okay, I don't know if I'm spelling it wrong, but oh yeah, I was spelling wrong. Okay, let's just make sure I'm spelling it wrong. Wait, I spelled adjacency wrong now. Adjacency. Oh no. Okay, you know, programmers are not always strong at spelling. Adjacency. Okay. So result list. Oh my god, I'm going to need to edit this out. If in degrees of result, of course. Sorry, if in degrees of course. So we want to check in degrees of course equals 0, not a result list. Okay, it accepted. Okay, so now that we've gone through it and fixed all of our really small and stupid spelling mistakes, let's submit it and see what happens. Nice. So it is runtime 96 milliseconds, and that's faster than 81.74% of Python 3 online submissions. So, pretty good stuff. And as always, thank you for tuning in. Like, comment, subscribe. This is my first ever YouTube tutorial video, so any constructive criticism is totally welcome. And stay tuned for more because I'm bored in quarantine. Thank you so much.